Hi, I'm James, and I'll be doing a walkthrough through Spring 2014 Midterm 2. That was last semester Professor Hilfinger taught the course, and so I thought it would be good practice. Just a warning, this is not going to be a comprehensive guide, and there will be things on the midterm that are not going to appear on this midterm. So let's get started with what would Python print. It's very, because these are worth almost a quarter of the points, it's very important to nail these and very important to draw pictures and really not make any careless mistakes. And so I'll walk through how to draw pictures for object-oriented programming. So let's get started. So let's read through the code. We have a Doge class, and so we're going to draw a box for Doge. We're going to write the class attributes and the methods it has. And so the class attribute, it has much, and then wow. Remember that the class attributes are right here. Methods, it only has a bark. Okay, this is just useful to keep track of things when we have inheritance. So let's draw our puppy class. Puppy. It inherits from Doge. So I'll draw a little arrow. It has its class attributes. It has vary. Methods. It has a init, and it has a bark. Okay, so this is so we ran through that code. Now let's create a Doge. So we draw a box. There are a couple ways to do this. This is just how I like to do it. You draw a box, you draw an arrow to point which class it's an instance of, and so Doge, this is called the init method. Notice how there's no init method in our Doge, but that's actually because I think it inherits from object, which has an init method, which just doesn't do anything really. So we drew a box. Okay, so that's that line. Such.much equals interesting. So this is really important that there's a difference between reference, or reference, I guess, versus assignment when it comes to class attributes. Notice how if we were to if we were to reference such.much, we would look in our such box. We don't find it in here, so we look to our class box, and we would return wow. But notice how we're assigning it here. So what actually happens is we create a instance variable, much, that is now going to be interesting. Sort of analogy is that let's just say we have a human class, and humans can all do something. I'm a human. I can access things that humans can do, but I can't actually change them. So I can't, me as an individual, I can't say James dot, like, I don't know what the human, breathe or something, and that's not going to change it for all humans. The same goes here. Such dot much is not going to change it for all the Doges. So that's that line. Now we create two more puppies, or puppies. So we're going to create a box for Fido. Draw an arrow, because it's an instance of the puppy. Run through the init method. There's no init. There is an init here, so we run through the code right here. So friend, give our Fido a friend. This is going to be what got passed in as friend, so that's such. And so friend is now going to point to such. Now we have a much. Much is going to be a list with two things in it. It's going to have Doge.much. Okay, so we go to our Doge class. Now we're accessing the class. The class attribute much. So this would be wow. Then the second the second element is friend.much. So we go here, we have a friend points to such.much is interesting. All right, so now we draw a flora, and I'll have to be careful. And we run through the init. Our friend is going to be Fido. Then our much is now going to point to a list with doge.wow. I mean doge.much, which is wow. And the second element is actually going to be friend.much. Well, our friend is Fido, and he has a much, which is this list. So could draw an arrow. Okay, you might think that this is a lot of work just to draw these pictures, but it'll make these what would Python prints a lot easier. So doge.much, we look into our doge class. We look at class attribute. It's wow. So wow. What the? Okay, wow. Pupye.much, we go to our pupye class. Does it have a much? It doesn't have a much. We go here, up to the parent class. Doge has a much, so it would be wow. Okay, so then we go to such.vary. So such is here. Oops. Does such have a vary attribute? No. So we look to the parent. Parent has a vary. Does parent have a vary attribute? No. We go to object, and object doesn't have a vary. So this will actually error. Saying Doge has no vary. Okay. Let's do this. Such.bark. So does such have a bark method? No. But it is important to check if such has an instance attribute called bark, because it might, and then this would call the bark. But yeah, so let's go to the parent, bark, it does, which points to this method right here. So let's call that method, which will return self.much. Well, self in our case is such, because that's doing the calling, actually, so this gets passed in as self under the hood, and much, so let's return self.much. It's interesting. So this right here will return interesting. And then we're going to index strings. And so this is inclusive and exclusive. So it'll actually return in, because the first two characters are in. Okay, so let's do Fido.bark. Let's go to Fido. Does Fido have a bark? No, but Pupye has a bark. So Pupye, it's right here. It'll be Pupye. We know it'll return Pupye plus whatever doge.bark self1 returns. And so let's call doge.bark, and then we're going to pass in self. So this is another way to call functions. Remember that there are two ways to call class functions. We could either say class.function and then pass in an instance, comma args, or we could call it an instance dot function and pass in the args. This is what we did here with such.bark. This is like that, and then doge.bark is like this. So we're going to be passing in the instances self, which is Fido. So we can write Fido. It's going to be our self. So when we call doge.bark, it's going to be passing in self here. So Fido is going to be going in as self in the bark method. And then it'll return Fido.much. Well, let's look at our picture. Fido.much points to a list. And let's get the first element here, which is interesting. So we can add strings together, and it'll come up with interesting. Okay, so Fido.friend.much, Fido is here, .friend, so we'll point now at such, .much is interesting. Okay, Fido.friend.bark, Fido.friend, so Fido's friend is such, such.bark, well, such doesn't have a bark method, but Doge has a bark method, so let's call such.bark, and that will return such.much right here, which will return interesting. Okay, let's do flora.friend.bark. So flora.friend is Fido, so we can actually just cross it out and write Fido. And then we've actually done Fido.bark before, so it'll just be the exact Pupye interesting. Interesting. It'll be the exact same as before. So let's scroll down a little bit. Flora.friend.much. Flora.friend. So this is now Fido. Fido.friend is such. So let's just cross all that out and write such. So this is just saying such.much, which is interesting because such is much attribute. Instance attribute is interesting. And that's the question. See, it's not so hard. Let me just make sure the answers are correct. Wow, error in. Puppy interesting, puppy interesting. Okay. Yeah, see, that wasn't so bad, right? Especially this picture really helps with the friend.much, whatever. So yeah, hopefully that wasn't too bad, and hopefully on the midterm you'll be able to get these what would Python output print, what would Python print problems. Okay, let's move on. I guess I can zoom in a little bit more. All right. Okay, so this is a list function, like a built-in list function question, just making sure that you know what map does. Yeah, so let's walk through. Basically just to remind you, map takes in a function and a iterable, I believe. And we've seen this usually with a list, but in our case, we're actually passing in a range, which it'll loop through all the numbers in that range starting with 0. And it'll apply the function to it. So, and it'll actually return, I believe, an iterable, or it'll return a map object. So this will return, this is getting a little nitty-gritty. You don't really need to know what this means, but it'll return some sort of map object, which we then cast into a tuple. So it'll get printed out. So let's walk through. So our function is going to take in some x. It'll return x, the index of x floor division to the element at that index of a if x is even. Else it'll return the floor division index, or it'll return the element at the floor division index of b. And we're going to be looping through range len ab. So let's write that out. So we're going to be looping through range len ab, and actually I'm just going to write it for the values we pass in. So we're passing in 2 tuples, which we can loop through, but the only difference is tuples are not mutable, but we're not mutating anywhere in here, so that's fine. So both of those are len, or together they're len 6. So we're going to be looping through range 6, which is basically means we're going to be going through 0, 1, 2, 3, 4, 5. Okay, so that's that right-hand side. We'll be looping through 0, 1, 2, 3, 4, 5, and then we'll be applying the function to it. So let's apply it to the first element. So x is now 0. If we first do the conditional check, if a mod 2 equals 0, that is true. A 0 mod 2 is 0. So we'll return this element, a 0 floor div 2, which is 0. So the index at element 0 is 10. So our final tuple is going to have 10 at the front. Then so we did that for 0. Now let's go to 1. Let's put a 1 here, put a 1 here. 1 mod 2 is not 0, so we'll return b of 1 mod 2, which is b of 0, which is 8. Okay, let's go to 2. 2 mod 2 is 0, so we'll return 2 floor div 2 of a, which is 1, and then we'll get the index of that, which is 5, and then 3. 3 mod 2 is 1. We'll get the index of b of 3 mod 2, which is b of 1, which is 7. And then you can see a pattern here, 25 and 11. So this is our answer. 10, 8, 5, 7, 25, 11. And just to make sure, 5, 7, 25, yeah. Okay. Environment diagram. All right. Will it all fit? I'll zoom out. Okay, so let's get started. A, remember you follow this indentation first. So A is 0, and they actually did the April function pointer, because whenever we def a function, we have to make an arrow to a function. And actually, parent equals global. That's important to note. Yeah. So now this is a function call. So we create a frame 1. The function is April. Remember, we always bind the formal parameters first before we go into the function. So the formal parameters are fools right here. You can find the formal parameters next to the name of the function. This points to, parent. Parent equals global. This points to a function lambda, which actually is defined in the parent frame. And actually, they don't have line numbers. Sometimes it's nice for lambdas to write the line number. Python tutor will do that just so we don't get confused. But yeah, so this is a parent equals. Actually, I'm going to write it takes in an x. Yeah. Okay, now we can actually go through the code here. Follow the indentation. A is 2. Joke points to a function, joke, where the parent is f1, because that's where we defined it. We don't go in there yet, so we continue down this indentation. If fools 777 equals 1, so that's a function call. We always create frames for function calls. The name of the function is not fools. We actually have to evaluate the operator then the operand. Fools points to this lambda function. So this is actually a lambda where the parent equals global, takes in an x. The x bound is 777. Does that make sense? Because now, so we evaluated the operator. Fools is a lambda. We evaluate the operand. It's 777. We pass 777 into our lambda, and then now we can actually walk through the function. So we're right here. A plus 1. So the return value is is A. Well, where is A? This is tricky because remember we have to look up parents for variable lookup. So A is 0 plus 1 is 1. So the return value is 1. So this whole thing right here evaluates 2. I'll cross it out, 1. So 1 does equal 1. Joke A plus 9. So that's another function call. Calling joke, and our function is actually called joke. Parent equals f1 right here, and our formal parameters are a. We pass in a plus 9, and a is 2 plus 9 is 11. So we pass in 11. Non-locals fools. So that what that does is that actually looks up the parents. It finds the closest instance of the variable name. And then now we can actually mutate it. So instead of creating another fools variable inside of f3, we can now mutate this fools. Note, non-local doesn't work for global. You can actually use the global keyword syntax that Professor Hilfinger introduced in lecture. Yeah, but is fools in global? It's actually in our f1 frame, so that's okay. So let's go to this line right here. Fools equals lambda y a plus 4. So we cross that out, and then we reassign fools to func lambda y. Parent equals now f3, because we actually defined this lambda function inside f3 frame. So yeah, and then we return a. So we return a, 11. Okay, so that does that line. So that value actually does have a return value of 11, but we're not assigning it, we're not printing it, so nothing actually happens. Okay, so let's go to this line, fools of April. So let's go F4. Fools, now we look at the operator and the operand. Well, fools actually got reassigned to lambda y. So we actually have to write lambda parent equals F3, because our lambda y has F3. Our formal parameters are y, and then y takes in April, which is actually a function. And so you follow variable lookups. You look up the parents. So parent is F3. Go to F3, is there an April here? No. We go to F1, is there an April here? No. We go to global, there is an April. So we actually point Y here. And then we return, what do we return? A plus 4, right? Because we're in this lambda, A plus 4. So A, we look up the parents, F3, A is 11, A plus 4 is 15. Cool. Okay. Zoom out. Okay, so draw box and pointers. Yeah, they did queue for us. So let's just get started. S, we draw a box. It has 3 elements. So you can index them. I don't know if they got points off if you did an index, but I think that's okay. So 1, 2, and then actually the third element is a list with 3 in it. Okay. Let's go to T. T is a list with 3 elements in it as well. 4. The second element is a list with S, which is here. So we point that here, and 5. It's really nice to point it to the front. I know this solution actually points it sort of like this, but Python Tutor will actually point to the front, and it's important to note that this arrow doesn't point to the first element, it points to the entire list. So yeah, and then 6. So 2, 0, I guess we can, oops, sorry. Wait, what? Okay, my bad. 1, 2, 0, 1. Okay. And then we draw U, which is just a single list with something pointing to T. So let's point to T in the front. Okay, so that's it. That's 5 points right there. Now, let's do U.append U. Remember, append is a mutation, so it actually changes what U is. So we actually add another element to the end, and we'll put an asterisk to show what we're changing, and then this will actually point to U. Yeah. All right, there we go. Okay, data abstraction. Albert loves to create salads. You want to make functional abstractions. This is really similar to what we did in discussion. So make vegetable. I guess we're using lists to create our vegetables. Then get name. So we're going to be passing in a list that has the format like this. So how can we get the name using list indexing? Well, we can say vegetable. We first have to get the first element to get this list, and then we have to get the first element. The 0th element, I guess, because it's 0 index. So we get the 0th element of the entire thing to get that first list, then we get the 0th index there. All right, so how can we get the color? It's the same thing, except now we start with the first element, and then we have to get the 0th element. Because the first will return that, the 0th will return that. Make salad. Now the format's a little different because it's not exactly the same. So to get the name, we have to do vegetable 0, 0. But then our vegetables, we only actually have to do vegetable of 1. Oh, oops. My bad. This should be salad. Because that's what we're passing in here. It doesn't know what a vegetable is, which makes sense because we're trying to make a salad anyways. Okay, that's that question. All right, so Stephen decides to use the data abstraction, but he messed up a bunch. So one thing, the first line right here, there are a bunch of things wrong. For example, you want to make a vegetable, I believe it says with 2 strings. yeah, yeah, you want to make a vegetable with a name and a color as strings. The fact that the fact that he used lists breaks the abstraction already because we don't know that vegetables are lists. And that's actually what he did right here, is he broke the abstraction barrier by indexing. Because although we know that vegetables are a list inside of a list, the whole point of data abstraction is that Stephen doesn't need to know that. So to fix this, we have to make vegetable with lettuce and green. And then the second index will be carrot and orange, but we want to make a vegetable. So make V with carrot and orange. I'm not going to spell it all out. Okay. Yeah, okay. And same with this thing. He actually broke abstraction barrier by indexing. We know ingredients is a list because, well, actually, yeah, we instantiate it as a list. So we're trying to get the first vegetable's color. Well, so the zeroth indexing will get the first vegetable color, but this stuff right here is bad. It's breaking abstraction barriers. So we actually want to do ingredients. Oh, actually, so we actually want to get the color. So we have a get color function that will take in the ingredients 0. Okay. Make salad, simple salad, ingredients plus make vegetable, cucumber, and green. That looks good because notice how we had use make salad. We use a string for the name of the salad, and then ingredients is going to be a list, and we didn't break any abstraction. Salad name equals lunch 0, 0. Okay, obviously breaking abstraction. We want that to be get salad name of lunch. All right. Okay, now we're going to be looping through, well, lunch 1 already is breaking abstraction. We want to be looping through the vegetables. So we can actually rewrite this as for vegetable in, and instead of saying lunch 1, we actually have a function get vegetables of lunch. And, okay. So that is now not breaking any abstractions. We can loop through a list because we know the vegetables are a list, or is a list. Yeah, so vegetable name equals get salad name XXX. This is not going to get the vegetable name because it's get salad name. So we actually, we want to rewrite that as get name of veg, which is going to be our variable that we'll be using through. Vegetable color, again, that's just breaking a bunch of abstraction. We want to say get color. Okay, print salad name. I have a vegetable color, vegetable name. That looks good to me. Yeah, last ingredient. We're trying to get the last ingredient of our list of vegetables. So we got the vegetables of our lunch. Len get vegetables lunch -1. That's not breaking any abstractions. We're just going to get the last element. And notice how there's a -1 just because if we want to get the last element, we need to find the length. But then because it's 0 indexed, move one closer. So yeah. Last ingredient dot name. Okay, so this dot notation makes no sense because we're using functions, not classes. So to get the name of the last ingredient, we use get name of last ingredient. Oh, sorry for the handwriting. Yeah. What meaningful variable could be used in place of XXX? Veg. For veg in get vegetables. Yeah. I guess because it's a salad, it doesn't have to be vegetables. But yeah, we gave points for that. Scroll down. Okay. All right, code writing questions. So usually this is where a lot of people lose points because what would Python print and environment diagrams are pretty formulaic, and that abstraction question wasn't too bad. So let's think about this question. Given a nested list of rLists, return the sum of all integers weighed by their depth. rLists are linked lists. Linked lists. I believe they're used interchangeably. But yeah, so some tips before getting started. Make sure you read everything they give you. We're going to need all this stuff right here. We're going to need the hint. Like, if they give you a hint, like, use it. Even with homework, too, or projects, if they give you a hint, it's usually easier if you use the hint. Obviously, there are different ways to do it, but that makes the most sense. And then now, I think this is where a lot of people feel intimidated. They don't read the doc test, or they don't fully understand the doc test. So you really want to understand the doc test, even draw it out. So I'm going to draw out the simple, and we'll figure out why that is, why that gets printed out. So simple is 1, 4, 6. Does everyone see why the nested sum is going to be 1 plus 4 plus 6? Because they're all the same depth. There's none of this deeper depth stuff. Okay, now we go to the harder one. I believe the harder one is the same as what is drawn here. If we just confirm rList 1, rList 1, rList of an rList, so that's creating a link where the first element is a link, 3, and then rList again, nested, nested, nested. Yeah, and then the 2 is just right there. So 1 times 1 plus 2 times 3 plus 3 times 4, because this is like depth 1, depth 2, and depth 3. Yeah, so we understand those doc tests. So let's think about how we can do this. We're probably going to have to recurse on the rest. That's really common in linked list questions. We're probably going to have to just the fact that they gave this hint sort of gets at that we're going to have to call something on the first element if it is a linked list, and don't call it if it isn't. Yeah, and we'll see in the solution. So I think to get really good at these code writing questions, I really think understanding homework 4 and homework 5, where there's a bunch of linked lists and a bunch of trees. I posted a walkthrough through homework 4. Yeah, I mean, it's just doing these types of problems over and over, and you sort of just spot the answer. And definitely, sometimes I'll just sit and stare at the question for 20 minutes. But hopefully something will come out of that. Okay, so we know the base case is usually if it's link.empty. That's like pretty common for link questions. And also, imagine we were to, oh, oops. We're not using classes. I already made a mistake. I didn't read this. We actually have to check if rList is empty rList. Instead of link.empty, that's classes. Yeah, so if we were to pass in an empty list, we should return 0 because there is no sum there. But also, this is useful because once we get to the end of any linked list at any depth, once we get to the end, we know that we can just add 0 to our previous sum, and that will stop our recursion. Again, the point of base case is stop recursion. So elif, and then now, basically, what I was saying before, if it's an instance of the, if our rList is an instance of the rList so actually, I don't think we can say is instance of rList because rList is not a class, and so we actually have to compare with the int class, I think. Oops. Though it might work the other way around. I haven't tested it, but the solution has int, and that's how I would have done it. So basically, this is saying if we are at some node where the first, oh, oops, or oops, we actually want to do it on the first, not the rList. Yeah, because we want to check is the first element a int. If it is an int, then we know we can just add that int to the sum. And so we know we're going to be using d as some sort of counter for our depth. So d times first of rList will multiply the depth we're at times the first list. And then actually we can't just leave it like that, because this might actually point somewhere else. And so we want to keep recursing on the rest. Does that make sense? So if we go back to our example, imagine we're at the first node. We have a 1, so we can add 1 to our sum. And then we actually want to continue with the rest here. We don't want to just stop. And sum at death, taking the leap of faith, it should return the sum of the rest. So we can just add our first 1 to it. OK. Now, pretend it's not a list. So we know if it's not an int. So now we recurse to the rest. Our first element is not an int. Well, what we want to do is actually we want to take the leap of faith and sum up the depth of our first list. And then actually what we want to do is we want to add 1 to the depth, because we know that if our first element is a list, or is a linked list, then that means we're going 1 deeper now. So we want to add 1 to D, but then we also can't forget about the rest of the elements of at that same depth. So going back to our example, that first thing will do this arrow, but then we can't forget about this. We need to sum up those as well. Yeah, and if you have time, I recommend run through your code, run through back in the doc test, and you might find that you're missing something. For example, if I didn't have that last line. Okay, binary trees. So hopefully you're getting comfortable with binary trees and binary search trees through homework 5. Should zoom, no, that's fine. So again, read through all this stuff. Whoops. BinTree is a label whose child is left and right. The empty BinTree.empty tree is the empty tree t.label. So this is a class implementation, as we can see with the dot notation. Write a function bound that takes in a binary search tree containing real numbers and 2 numbers low and high. It returns a binary search tree that contains all and only the elements that are between high inclusive. Okay. So this is basically like a doc test, except they just drew it out for us instead of write it in code. And so this is calling bound tree 410. So as I was saying before, make sure you understand the doc tests. Bound tree 410. Okay, all of this stuff is below 4. All of this stuff is greater than 10. And so we just stick those on. 4, 5, yeah. Okay. Again, our base cases. Usually if we hit the empty tree, again, this is not always the case, but the fact that we're sort of traversing a tree, what gives it away actually is that the fact that we're building a new tree, So once we hit the bottom, once we recurse to the bottom, for example, the empty trees here, we actually want to return BinTree.empty, because ideally we would have built a new tree that had the 6 as the label and then the recursive leap for both of those. Anyways, return, if BinTree, again, I keep making mistakes. This should return BinTree.empty, but we really want to compare is tree is empty. So they actually give us a function to do that. You could also say if tree equals BinTree.empty, return BinTree.empty. elif, so now we want to run through and say, okay, now we're going to be doing the cutting off part. So imagine we are at this node right here. Imagine if this node is less than the low, or I guess rather, let's draw the 3 back here. So imagine we're on this with this node right here. This 3 is less than the 4, and so what we want to do is actually we want to cut this node off and just actually only go to the nodes on the right. And the reason why we actually have to go to the nodes on the right is, what if this 4 was a 5, this was a 3, and then there was actually a 4 right here. 5 is not less than 4, but 3 is less than 4, but this 4 right here is still greater than 3, but less than 4, and so we want to keep that 4 there. So that will take care of this case. If tree.label is less than low, then we want to actually return tree.right. However, again, we want to be doing, we don't know if there are other numbers in our right tree that are less than or greater than our low and high, and so we actually want to recursively call it on tree.right. Okay, and we want to do the same logic if it's greater than high, but instead we only want to do it on tree.left. Yeah. Oh, whoops! I forgot to include the. I forgot to include the other arguments for the recursive call. Okay, comma, low, high, because we don't change low or high ever. Okay, but now, if none of those cases are true, for example, let's just say we're at the top of the tree. 8 is not less than 4 or 10, or greater than 10. We actually want to return a BinTree with the tree.label, and then we want to call bound on tree.left, and then LH, low and high, comma, bound tree.right, comma, LH. And if we look up, we just want to make sure BinTree constructor takes in a left and a right. So we want to make sure we're passing in a left, comma, a right. Okay, ooh, we're almost done. Sum of human knowledge, I don't know that. You can try to figure it out. Maybe it has something to do with physics, I'm not sure. Most people don't get that point. Big theta, all right. So in this test and also in a lot of past material, they used theta, but we actually taught you big O. Just to reiterate, theta means exactly this runtime. So n. This says less than or equal to n. Theta is like the exact bound. So if we know if something runs exactly in n time, we can say theta. If we know that it runs in n time or it might run a little faster, then we can use big O. And in the real world and in interviews and in other classes, they sort of use these interchangeably anyways, so it's not a big deal if you don't know the difference. But yeah, all right, so let's run through our code here. Let's see what it does. We have an unmatches S. We create a set. We loop through all the elements of S, which is a list. If the item is already in our set, we we remove it, else we add it, and then we return our set. So fill in the blank. The function unmatches returns a set of all, and then basically you want to think, okay, we're removing we're looping through S. If the item's already in our set, we're going to remove it, else we're going to add it. But if we were to add it, then if we found that element again, we would remove it. So for example, we had a list with like 1 and 1. The first time around, we're going to be at 1. We're going to add 1 to our list, or to our set. Then the second time around, we're going to remove it. So unmatches is actually only going to have a set of all elements that occur odd number of times in S. Basically, if there was a third one here, then it would add it, it would remove it, then it would add it to our set. And that logic applies to all other if it was like 1, 1, 2, 2, or something. Yeah. Okay. Let's assume the operations of adding to, removing from, or checking containment in a set takes roughly constant time. This is actually really useful knowledge, and actually I introduced that in homework as well, that constant time. That means it's really fast. So sets are really, really great. Given asymptotic bound on the worst case time for unmatches as a function of n equals len s. So we walk through our code for item in S. So we already know that we're going to be looping through every element in S. So as S gets bigger, we're going to have to loop through more things. And a for loop runs in theta n time, because as n gets bigger, n, if you add 1 to n, you're going to have to loop through one more element. So we know that, and we walk through the rest of these. If item in result, that runs in O of constant time, constant time, constant time. So we're going to be looping through every element in S doing constant time work. So it'll actually be theta of n, or big O of n. Doesn't really matter. I guess capital N. Yeah. All right. Suppose instead of having result be a set, we make it a list. And so append, which is the same as add. So append equals constant. Remove / in equals L, where L is the length of set. So already that sort of in my mind comes out to theta of n squared, because of the fact that we're going to be looping through n elements, and for every element we're going to be doing something that's going to take theta of L time. The actual reasoning why it's n squared is because, for example, let's just say we have a set, 1, 2, 3, 4. We'll be looping through each element, 1. We'll add that to our result list. So result is now going to have a 1. So append is constant time. So the first iteration, it'll be constant time. But then we loop through one more element, 2. We have to first check if it's in our L, our result, which right now only has length 1. So it'll be, it'll take one run, or it'll take a theta of 1 to find the 2. So we put the 2. And then actually, when we go to the 3, it'll take theta of 2 times when we put the 3. And then 4, it'll take theta of 3 times to check, check, what do you call it? To check if our element's an in. And so what'll actually happen, if we can draw it out, whoops, I don't have room, is for every element, result will be getting 1 bigger. And so for every element, so let's just say we're going this way with elements, and then we're going this way with the L, and it'll actually sort of look like a pyramid, where every time L will be getting bigger, and we'll have to be looking at more things. And so when we increase n by 1, L actually will get bigger by 1, and we'll actually have to be doing another, I should draw this out. Runtime's pretty important. Okay, maybe there's some room in here. Okay, that's fine. So this is 6C. Basically, if you actually want to break it down, L is going to be so the first time it'll be n minus whoops, the length will be n minus theta of, basically, yeah, we're going to be doing something that'll take n times for each element in the set. Yeah. Sorry, that's not the best explanation. I might post a follow-up with a better explanation or some sort of visual. I just want to finish the last question. We're almost done. So suppose we only, suppose we only consider the cases where the number of different values in S is at most 100. We use the list for result. So we know that the number of unique values in S is less than or equal to 100. That means the size of L is going to be at most 100, because if there are duplicates, then, like, where does it say? Since we know each value appears at most once in our L, or in our result, so len result is going to be less than or equal to 100. So that means every time we have to check our in operator or our remove operator, we know it's going to take theta of 100 times, which is basically theta constant time. Because we know L can never get more than 100. That's different than part C, where L could be equal to n at any given point. And actually the worst case for C, worst case is no repeats. Where basically we keep adding to our set, or our list result, and there's no repeats, so we keep adding, and the length of L is actually just bound by n, and that's why it's n squared, because at the worst, L could be n, and then we have to do n calls. However, in this problem, we know L is actually bound by 100, so we know we'll never have to do more than 100 calls. Or it won't take more than 100 theta of 100. So that means that actually our function is going to run in n time, because for each element, we're only going to be doing basically a constant amount of work, because L won't actually get more than 100. So basically, you can think for item in result, do something. So like actually, this is going to bleed into the where my head's going to be. For item in result, you're going to be doing something that'll take theta of 100 times each time, which is basically constant time, which is similar to part B, where basically we did something in constant time every single time. Okay, so hopefully that helped a little bit. Runtime is not going to be as big a portion of the test. As we can see here, it was only 4 points compared to what would Python output, and all the rest were a lot more points. But yeah, hopefully this walkthrough was informative. Please post a follow-up if anything was confusing. And yeah, good luck on studying.